Uh, Welcome everybody at this P4 Developer Days session. So today's Monchen and Francois are going to present their work called P4Muse. Monchen recently got his PhD at Polytechnique of Montreal, University of Polytechnique of Montreal, while Francois is professor at this university. And thank you guys for joining the P4 Developer Days and support the P4 community. Before to start, few information. So the session is going to be recorded and will be available on p4.org and the P4 YouTube channel together with the slide. And then if you want to ask question, please wait the presentation wait the end of the presentation, and then you can use the chat or open the mic and ask question. But if you do the voice part, please open also your camera. And then Monchen, the floor is yours.
Merci, thank you so much for setting this meeting, and thank you for joining us to this presentation. We want to present P4Muse. It is a framework for bringing modularity to P4 by compiler manage without syntax modification. And also, I want to thank you to say thank you to other author of this work, Francois, Bill, Ivan, and Jean-Pierre. Okay. The outline of this presentation includes a problem statement, related works, research questions we have, and after that, research objectives. Firstly, we present modularity for the parser. As the work we present in the P4 workshop, modular code parser for the P4 language, and after that, present compiler managed P4 modularity, especially we did this in the P4Muse. And at the end, we mentioned conclusion, limitations, and future research and publications. Okay. For the problem statement, current P4 programs are monolithic and hard to reuse. For example, if we have two P4 codes, for example, the programmer in the firewall code wants to reuse Ethernet and IP version 4 code from another code. It is hard, and it needs to create it again. And also I want to mention the importance of modularity in the P4. For example, modern data plane are large, complex, and rapidly evolving. So it reduces, with modularity, it reduces programming time, and it creates less error-prone codes. And also modularity is in the protocol stack. For example, IP version 4 uses Ethernet protocol, or UDP and TCP use IP version 4. So if we have modularity, we can handle these situations in protocol stack better and in an easier way. And also the benefit of using a vendor code along with customer codes, call it incremental programming, because a vendor knows hardware better than customer, and customer sometimes needs to create their own codes along with using vendor codes. So modularity helps this situation. The reason P4 from scratch does not have modularity, complete modularity, because people try to keep P4 as simple, and simplicity in the P4 is so important. So when we want to add modularity to the P4, it's important to keep a balance between simplicity and modularity. Uh, okay, going to related books. Uh, we have two great books, Mako P4 and Lira. Uh, they bring modularity to P4. For example, for Mako P4, homogenize everything into match action. But it impacts on architecture, IR, and syntax, and also for Lira, do the same thing with different approach. For example, hide low-level people code with a one big pipeline and impacting architecture, IR, and syntax. And also we have deploy and P4Weaver. For example, for deploy, we have provided GUI for incremental programming. And for P4Weaver, they used annotation system and Antler as a parser generator for incremental programming. And at the end, we have P4Ansible. It is non-complete book as the code they mentioned in their GitHubs. And also they could add new syntax for inheritance, especially in Bison parser generator of the P4 compiler, but not in the IR of the P4 compiler. So we firstly we try to classify the important features we consider in this work, in related works. At the first, automatic merging. For example, each of them do not have the automatic merging. And in the second feature, backward compatibility, for example, Mako P4 could not reuse previous P4 codes, existing P4 codes. Lira does not mention it, and other can do it. And also vendor customer compatibility. Mako P4 and Lira do not mention it. And because it's important for us to understand the lack of people language for bringing modularity. So it's important for us to see this by doing modularity without new syntax or annotation. But all of them use new syntax or annotation and also does not interact with P4IR directly. And also about inheritance, just P4Ansible has inheritance for some constructs of the people. As I mentioned, it is not complete rule. And it is not in the P4IR, it is in the Bison parser generator. So we have two main research questions for the whole of my PhD. Firstly, can modularity be introduced in the P4 language using its existing compiler and language without adding new syntax or annotation? It is the main question of the P4Muse. And for the second work, at this time, it is under review. Can object-oriented style inheritance be added to P4 and give more modularity? And also, I mentioned the link between the first work and second work and why we did this, the second work. Okay, about research objective, so we want to have P4 modularity by merging P4 code instead of modifying its syntax, and also keep the backward compatibility in the parser and the rest of the pizza in the second part. Okay, going to first part of this work, we present in the P4 workshop as a modular code parser. And we consider modularity in the parser part of the pizza. So at the first, as you can see in the base code, we include the extension P4 code. And in the front end, we add three passes for resolving names of the parser, comparing parser graphs, and merging parser graphs. And at the end, we can have a merge parser output. So for the first passes as a resolving names, for example, if we have two parser, for example, we mention it as a first parser and second parser, and we can call it in during this presentation as a base parser and extension parser. We can have a different input and output with different names, I mean. So in the first one, it is packet. In the second one, is it packet on the line two. So if we want to merging two parser, it is mm, we need to consider different names. So the compiler, these passes of the compiler can understand the corresponding name in the base parser and resolve the name of the second parser to the base parser. So as you can see in the second parser as an output, we have a packet instead of packet underline two. And can do this for the whole of the parser, not just the input and output. I mean, use this name for input and output during the program. As an outcome of this work, for example, if we have two parser graph, for example, for processing TCP and in the middle for processing UDP, we do not consider the name of the states because we understand a programmer can use different names for the states of the um, of the node. So for these situations, we use we firstly we define different nodes. For example, as a equivalent node, we consider two nodes with the same transition number and same the header they extract, and also transition number of children of that node. So in that situation, two nodes are equivalent. If we have the same header they extract and same transition value, we consider as a mergeable because we can merge their children. And if they do not have the two first conditions, we consider them as a different node. So based on this definition, we could consider different names for the states. And as an output, we have this one. The base parser. A compiler can understand the base parser does not have the UDP as an extra state in the base parser, so try to merge it as the children of parse underline IP version 4. So because we have the equivalent node in the parse underline IP version 4, the compiler merge UDP as the children of parse underline IP version 4 in the base parser. So this is the output of this work. And for the P4Muse, we reuse this part of P4 workshop with add verifications of the merging parser and other things, and also doing this for the rest of the pizza architectures. Firstly, like the previous work, we include the extension P4 code in the base code, and also we consider three interface for P4Muse. For example, code reusability. It is like when you want to reuse the code of another programmer. So P4Muse can merge that code to your code. And also we have two other interface, sorry, two other interface, I mean data plane, pipeline composability, and vendor customer framework. And we mention it in the next slides. And in the front end, we have passes for parser, struct and header, the parser, action, table, and apply part. And in the mid end, we have some passes for verification of merging, for example, for parser of control flow graph analyzer, applies control flow graph analyzer, and shared data analyzer. For example, for control flow graph, we compare the base, extension, and merge control flow graph for apply part and for the parser part and mention it as the analyzing log because programmer can understand which part we could merge and which part we keep both constructs, for example. And also we have some shared data in two or more P4 code, for example, for egress port. They are so important for verification part of the merging two or more P4 codes. So also we mention it in the analyzing log. And also at the end of the midend, we could have merge P4 code. And at the end of the backend, we could have merge output, for example, JSON configuration. Okay. So for the parser part of the P4Muse, I mentioned another examples. For example, if we want to merge parsing IP version 4 with advanced tunnel, as you can see, Ethernet is the equivalent, or two Ethernet are equivalent node. But parse underline my tunnel as a child of Ethernet is not in the base parser. So compiler try to add it. But when try to add a mergeable node, like parse underline my tunnel, sorry, as a different node, it needs to also merge its children. For example, parse underline IP version 4. But because we have parse underline IP version 4 in the base parser as an equivalent node, so keep it in the base and just merge parse underline my tunnel to the merge parser. Okay, this is for the parser part. And also we use the information we receive from the comparing of the two parser, I mean two final state machine of the parser, and use it in the merging struct header and the parser part. For example, in the left you can see merge parser states. And as you can see, I mentioned it with purple line, type underline my tunnel, column parse underline my tunnel, and mention it as the children of parse Ethernet, like the previous slides. And also a compiler merge state of the parse underline my tunnel. I mentioned it with blue part. So compiler can understand which header this merged states use and extract. For example, htr.mytunnel. And also in the first part of the program, we have htr. I mean out htr's htr. And compiler can understand the connection between them, and based on this connection, can merge the corresponding struct of these states. I mean, my tunnel underline T, my tunnel from the extension code. And based on this, also can merge the header of the corresponding header from extension code to the base code. I mean, header, my tunnel underline T. And at the same time can merge the deparser state of the corresponding state. I mean, packet.emit htr.mytunnel. So based on the information we receive from comparing finance state machine, we can uh, merge a struct, header, and deparser. Okay, but also we have some problems. For example, about header modularity. For example, we can have two IP version 4 with two versions. For example, 6-bit diff serves and 2 bits ECN in the left and 8-bit diff serves in the right. And maybe the extension code use one of them and base code use another version. So this situation shows us it's good to have a union to solve such problem. As far as I know, P4 has union, but not for subcomponent of the header. It has for header parts. And for this situation, for solving these situations, we keep the version with different parts. For example, 6-bit diff serves and 2-bit ECN, and the part of code wants to use to another version, compiler concatenated those parts and create the new one, create another version, and solve this problem. And about table action and apply modularity. For this part, firstly, we started with action part. We compare actions one by one, and for example, line by line recursively. If we have the same actions, we keep the compiler keeps one of them. And about table, compare recursively, firstly, key, size, default action, and the name of actions that table uses. And if they are the same table, the compiler keeps one of them. And also about apply block parts, compare line by line recursively. It usually includes condition, if condition, and applying table. So if it has the same, I mean, we have the same apply block, keep one of them in the apply part of the people code. But as you can see in this part, we cannot merge, for example, two actions with some differences, or two table with some differences, for example, with different size. And we try to solve it in the next work. Okay, going to modularity level. Also, we define 3 level of modularity. For example, construct level modularity, for example, merging two tables or merging two headers. Protocol level modularity, for example, merging IP version 4 protocol with IP version 6 protocol. And also it could be not just for the parser part, it could be for the whole of the P4 code. I mean, one IP version 4 protocol can have a parser, header, struct, the parser states, and also table and action. So we can consider it in this level. And also application level modularity, for example, merging firewall with tunnel code. And if you remember, we mentioned to interface data plane pipeline composability and vendor customer framework in this slide. As you can see, we have a server client architecture, and network manager wants to create some P4 code, some trivial P4 code, but wants to reuse built-in P4 functions, P4 codes, without rewrite them. So just mentioned, for example, I want advanced tunnel and firewall to the server, and in the server, P4Muse can merge advanced tunnel and firewall and any P4 codes and create merge code and send to the client side, and network manager can use it. And also we have a vendor customer framework, and we implement for P4Muse because, for example, P4 Weaver creates it for the first time, and we implement it for P4Muse. For example, it is in this client server. For example, a programmer sent customer code to the vendor or to the server, and in the server, P4Muse can merge vendor code with customer code and create merge output, not merge code, to prevent from showing vendor code to the customer. So customer can reuse vendor code without seeing it and also use it. Okay, going to results of this work. We try like related work. We try to mention lines of code as one of the important feature for showing the mm, benefits of modularity. We classify in three parts. I mean, header and struct together, parser and deparser together, ingress and egress together. Uh, for example, and also we have 6 case studies: IP version 4, IP version 6, firewall tunnel, quality of service and firewall, tunnel and quality of service. And in the case 5, we have firewall, tunnel, quality of service to show we can merge any P4 codes we want with P4Muse. And at the end, we use service 6 and NDP to show P4Muse can handle complex applications. And for this one, I mean, for 5 case study, we use Mininet and BMV2. And for the last one, also we use ONOS. Sorry. And as you can see, the improvement in all of them. We have improvement in all of them, and especially in the case we have the same constructs. I mean, for example, in header structs, if in the cases we have the same header and structs, we have improvement because we keep one of them. Okay, going to performance analysis, we compare latency and reciprocal throughput. For example, for latency, as you can see, we have improvement in all case studies. We and for I need to mention for individual code for the first row. We run, for example, we run IP version 4 and then we run IP version 6. And for the second row, we run the merge code, IP version 6 and IP version 4. This is for latency, and this is for reciprocal throughput. And as you can see, we have improvement in all of them, especially for the complex one. because in the complex one, it shows benefits better than the simpler codes. Okay, and also I need to mention P4Muse is designed and validated in V1 model, but we consider the we consider supports for other architectures in the design. For example, in V1 model in the left, as you can see, we have two V1 switch, which includes base parser, base verify checksum, base ingress, base egress, and compute checksum and deparser. So at the first, we compare two main V1 switch, and recursively goes on that and compare to base parser with extension parser, and then verify checksum with another verify checksum, ingress with another ingress until the end. And we can do the same thing for other architectures. For example, for PSA, we have two base IP and base EP, and in another code we have extension IP and extension EP, and in each of them we have ingress parser, ingress deparser. For example, sorry, and we can recursively compare them like V1 model. And also in TNA, we have the same recursive method. So we can use P4Muse in other architecture. I do not access to Tofino to validate this method, but we consider this support in the design from the first. And for the second question of this research, I mean, need of object-oriented system in the P4. For example, in P4Muse, we can just support modularity at the table level, as I mentioned. For example, we can just keep one table if two tables are the same, and lack of a mechanism to reuse subcomponents within a table. So in the next study, introduce inheritance to enable fine-grained modularity, and it is under review. This work, P402, is under review at this time, and also presented in my thesis. And about the key finding of this work, modularity reduce lines of code by an average of 33%. For example, in SRv6 with NDP, improves throughput by up to 45, for example, in SRv6 with NDP, and enabling multi-program execution in one program, for example, in tunnel, quality of service, and firewall. And going to limitations, it is in the static modularity only. As you know, we have a lot of works about the runtime and data plane programming. So it's good to consider such works for runtime works because it's important for them. I mean, modularity in the runtime for such works. And also evaluation limited to reference architecture, as I mentioned, for V1 model. So it's good to do it for other architectures. And also tooling and ecosystem integration. This work and also second work, as I mentioned, for inheritance, I think it is good if we can add it to the P4. And about future research, as I mentioned, it is good for dynamic and runtime modularity, standardization, and ecosystem integration, and also modularity across control plane parts. I know it is based on the, for example, Python or Java or something like, regular programming languages, but consider them in the control plane also is important. And about the publications, firstly, we present the modular code parser in the P4 workshop, and then P4Muse in IEEE Access, and the second work, third work in the P402 on the revision of the IEEE Access. This is the reference, and thank you for listening this presentation, and I'm ready for any questions.
Thank you so much for the presentation, Mohsen. So uh, I have a question, and is what motivated you to work on modularity in P4, and what gap did you see in the existing approaches?
Uh, because existing approaches, we believe we cannot, they do not use people directly. So they could not understand the problem of the modularity, the lack of the modularity in the P4. So we understand it's better to start inside of the P4 with P4IR and understand these lags uh, inside of the P4 and try to solve it. And because, as I mentioned, we understand we need to keep the simplicity of the P4. So based on these lags, we can understand what thing we need to add to the P4. Which syntax, for example, for inheritance, we need to add to the P4.
Thank you for the answer. I don't know if there are questions from the audience.
Yeah, thanks, Mohsen, for the presentation. So you showed, I have a few random questions. You showed some performance numbers. Were those running like on BMV2 or something? Yeah, so that was running on BMV2 target. Is that correct?
Yes, BMV2 and Minimatis.
So I didn't understand how you could get a performance improvement based on this approach. You know, if you're merging two codes, I would think the performance would depend on, you know, like if the pipeline got longer or something. Why would merging the code result in a performance improvement?
Because, for example, as I mentioned, we try to implement individually. For example, for each case study we try to implement it individually in BMV2, and also implement the merge one by using merge P4 code we received from the P4Muse. As you know, we try to reuse the control plane part also with no changes or minimal changes, control plane part of the individual code, because P4Muse can merge, P4 code cannot merge the control plane part. So this is the way we implement it.
Yeah, I can add something on that. If you look at the left columns of each, those that are paler green,
Yeah.
you have two stacked columns. One is the base code, the other is the extension code. So if we don't merge the code, we have like two codes that are running. So it takes more resources because we actually run two codes, two complete codes. when we merge, we have a lot of code in common that is removed, so the total amount in the right column is less than the total in the total amount in the right column is less than the total in the left. But if you take individual codes in the left, you will see that the right column is a little bit higher than individual columns on the left. So the IPv6 plus IPv4 is, well, a little bit slower, but almost exactly the same as the IPv4 on the left column. So if you were running each code separately, you would have almost the same performance as merging them. This is what we see here, that in fact merging does not increase much compared to one of the base codes. But if you run both base codes, then you have duplicated code, and then you lose time doing same things twice. Okay. The only one that we actually seem to see benefit is from the SRv6 plus NDP, but it's because when we do the test and we have merged both, we do like an average. So if some packets pass in SRv6 and some pass in NDP, then we don't have always the SRv6 latency. We sometimes have the NDP latency. So it's kind of an average between the both.
Okay. What does it mean to run two codes? Maybe I'm misunderstanding. You're merging two, you're kind of splicing together two pipelines to get one composite pipeline. How can you run them separately in a test?
In a test, to run them separately, we actually just run them separately and put the millisecond of one and put the millisecond of the other one above the other. So it's two columns. So it's a sum of the milliseconds of two things.
Okay. Yeah, I guess I don't understand how that relates to the real world where you run two separate pipelines sequentially.
Well, if you would really run them in the real world sequentially, will it do that? Probably no architecture will be able to run them really sequentially. Maybe they will run them in parallel by using twice the resources, so maybe it will not give those values. It's not obvious how it would actually run it. So it's mostly seeing that merging does not add much overhead compared to the base codes, and that it's less than the sum of the base codes.
That makes sense.
Yeah.
Okay. Another question is, do you have any like three-way diffs that show side by side like the original code, extension code, and what the merge looks like? That would be easy to visualize what the tool is doing in terms of merging the code. Have you ever tried to look at like a three-way code merge or a code diff? Yeah, so merge.
This one?
Yeah, this is, you probably don't have it handy, but I'm saying from the standpoint of being able to see the code, like, you know, the real full code, showing a three-way merge, which code editors can often do, or diff tools, would be very useful to see how, okay, I can see how one code base and the other merged into the outcome, you know, line by line kind of thing. Just it would be interesting. Maybe you have that.
I think we have it in the paper.
Okay.
Yes. For example. Yes. If I just.
Okay. Yeah, I see that. A little easier. Yeah, the slide was more condensed.
Yes. The first one at the left is the advanced tunnel. In the middle we have forward, and in the right we have the merge code. And yes, for example, I show for example, TCP transition to the from IP to the TCP with purple, and also TCP with blue. And you can see in the merge we have TCP. I mean, the compiler merged TCP to the base code, because in the base code we do not have a state for TCP, and also merge this transition. Yes. Yes, and we consider this improvement in lines of codes results. I mean, the number of the lines of codes, the improvement in the lines. Yes.
Yeah. Okay. So you showed early on when you were looking at the two parsers, you reconciled the name differences of the parameters in the parser, right? You figured out, well, these have the same signature, but maybe a different symbolic name, but they really mean the same thing, and you merge them. Now, how about when you have header structures, right? There's a lot of flexibility in what people name the headers. They're arbitrary. You have a header containing like an overall structure containing all the different packet header types. How do you also have to resolve that as well and try to make sense of two different naming schemes for headers?
For example, in headers, if I find, yes. For example, in the header parts, we have the resolving name path for all parts, not just for the parser. I mentioned for the parser because at the first we presented in the P4 workshop work, but in the P4Muse we have it for all parts. For example, if in these examples, if we have for the first one it is version, and for the second one it is version underline, for example, underline 1, for example. Based on the size and based on the places of that part, a compiler can compare recursively. I mean, understand between bit 0 to 3. In the first one, we have version, and bit 0 and 3. In the second one, we have version underline 1. So change version underline 1 to version, the whole program in the extension code. So resolve, yes.
Those are the fields inside struct head HDR. But what if the structs are named differently? What if one of them's named HDR and the other's named header, HEADER? Can Muse figure that out? You can name them whenever you want.
I want to, if I find, it is, for example, it is like input and output of the parser. As I mentioned, we have resolving name for example, for header. For example, in this, yes. For example, if we have, yes, if we have struct headers, and in the base code, and we have struct headers underline in the second code, compiler can understand corresponding struct with the another one and change the struct headers underline to headers, and also
so
for
you
other
kind of solve this problem generally.
Yes.
Interesting. Well, I probably should have read the paper just to get some background, so I'm not asking all these dumb questions. But what's the tool? How was the tool implemented? Is it P4C, or you have external tool?
No, it is in P4C because we wanted to use P4IR directly and understand what is the problem we have in the P4IR when we want to add modularity to the P4. And also in some part of the paper, we mentioned the problems. For example, as I mentioned, we do not have union for subcomponents of the header in the P4 language. So it's good.
Is there an intent to try to add this capability to P4C, to do a merge request into the repo? Or is this more just like an experiment?
Yeah, we add different passes to front end of the P4C and mid end of the P4C. to handle merging and also consider verification of the merging.
I mean, I don't think I asked the question very well. Did you want to contribute this to the open source P4C compiler?
Yes.
Like do a merge request into the repo?
Yes, we use P4C, but yet we could not make it open source, but we want to do it as soon as possible, especially for the second work. We believe maybe it's more important because we bring inheritance to the P4 and we try to keep it open source as soon as possible.
Yes, the goal is to eventually have it open source, and probably if P4 community accept it, it could be merged in the actual P4. It would be better than to have it separately, but it might be difficult to make it.
Yeah,
I'm not sure how they are open to these kind of additions.
Yeah, the barrier is a little high. I haven't worked in the language design group for a long time, and P4C is mostly maintained by people in that group. But I would think there'd be at least interest in this. That more of them are in this meeting. No, this is good. I've been playing around with Claude and Copilot and tools like that, and it would be interesting. They're so powerful now to ask it some questions about this project, or let's say get some insights, like what would it do to solve this problem? Just out of curiosity. I think it would be very illuminating. The tools are astonishingly powerful now. And I don't know if there's enough P4 code in the open source community that Claude has been able to incorporate into its language model. But there has been a lot of open source P4 code, for some time. You might just, for fun, try it out. Ask it to merge two programs and see what it does. It might give you ideas that you had never thought of, surprisingly.
Yeah, because I think it is not so hard, especially for not complex applications, but maybe we can have some conflicts between two or more functionalities.
Yeah.
For example, we had this about, for example, firewall and tunnel. One of them wants to forward, one of them wants to block that packets. Because of that, we add different verification paths. As I mentioned about comparing control flow graph and comparing shared data between two or more P4 codes to understand such conflicts when we merge. Yes.
Yeah, I can see how an AI agent might help you identify, something you can't resolve with the C++ code, and it has to give the user choices with insights into what the outcomes of those choices are. I'm not trying to redesign it for you, but I've had a lot of fun with Claude, and sometimes it's very helpful.
Yeah, it's very interesting to see what code it generates, and sometimes how it fails to generate code. But
oh yeah, you can spend hours telling it to do something that any programmer would figure out, but then other times it writes thousands of lines for you. It's just boring code, right?
Yes.
Especially if it's just really routine.
I never tried to make it generate P4 code. Like you said, there's not as much P4 code. Like he's very good. Well, most of these AI are very good to generate Python. And when you ask them to generate like C++20 code, there's more errors in that. So maybe P4 is even worse than C++20. I'm not sure, but
yeah. Well, cool. What's your next step, Mosen? What are you going to do next?
Yes. Actually, at this time, I'm looking for a job. Maybe industrial or maybe academic. It depends. But I like to apply these things in the industry. And also I want to complete the second work. I mean, as I mentioned, make it open source and maybe use it in the P4. Yeah.
Nice.
Thank you so much.
Nice.
Thanks for the talk.
Yeah, I think that we can close here. Thank you again for the talk. It was very interesting.
Thank you so much.
Before to close, the next P4 Developer Days will be the 19th of March, and the title is P4 Split. And thank you again for presenting your work, and have a nice day.
So P4 split is the reverse of what we're doing. Instead of merging, we split. Good.
All right.
Okay.
Have a nice day.
Have a nice day.
Have a nice
Bye.
day. Bye.
Seeing you
Bye.
again.
Bye.
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 Bye.